Okay, good afternoon, all of you. Any questions from previous classes? I sent a message to you that quiz 2 is going to be on 18th November. Okay, similar to quiz 1. The timing and other things. And for genuine reasons, if you require extension of deadline, that may be considered. Okay. Professor Ramlan, you want to add something?
No, I think that is okay. You start, then I will join in.
And here, including today's class, we have 2 days left. So I want to just give an introduction to design of columns. Please note that as a part of basic course, this basic course, we touched upon some of the basic concepts, more advanced things about whatever concepts you learn. Maybe you may be learning as a part of advanced courses if you take them. Okay, and let's start. So the next topic is columns. Okay, before we proceed with the details of this, I just want to show you some information related to this columns. If you see IS 456, page 48-49, they are giving specifications for these reinforcement related to columns, longitudinal reinforcement as well as transverse reinforcement. Here, longitudinal reinforcement for columns. Okay, what are the requirements? You have whatever spacing or whatever size of the rebars and percentage of steel, similar kind of clauses are there for this columns as well, reinforcement related to columns. This is for longitudinal reinforcement and transverse reinforcement, and also how to arrange this transverse reinforcement. And when you have this, when the size of the column increases, okay, transverse reinforcement, how to arrange, all those details are given here. And in addition, what should be the spacing of the transverse reinforcement? That spacing of the transverse reinforcement is usually referred to as pitch. It is nothing but distance in the of the reinforcement in the transverse direction. And what should be the diameter? And transverse reinforcement can be in the form of ties or stirrups. Okay, you as a part of your design for shear for the beams, design of beams for shear, you know, you learned about these stirrups, vertical stirrups, inclined stirrups, such kind of things. So those kind of stirrups you can have, and usually they are referred to as ties in when you talk about columns. Those stirrups are referred to as ties in the lateral direction. Okay, lateral ties or polygonal links. Okay, depending on the shape of the cross section of the column. So this is nothing but transverse reinforcement. And there is another kind of transverse reinforcement. Instead of having separate ties, you can have a reinforcement, transverse reinforcement, continuous one in the form of a helix or helical reinforcement. What are the specifications related to that? They are given here. Anyway, in a way, columns can be classified with respect to the based on the reinforcement as well. We'll see that in a while. Okay, so page 48-49 gives you the reinforcement specifications, and 48-49 and also 50 you can say this page. Okay, because this gives you the reinforcement, how to provide the transverse reinforcement and other things. So 48, 49, 50 gives you idea about the specification for the reinforcement and limit state of collapse under compression here. This gives you, that is page 70 and 71 and even part of 72 talks about this, the design details. What are the equations, what are the assumptions that are made in the this design of or the theory, or how these equations and other things for design purpose, how they are developed, what are the assumptions and other things, they are given here. Okay, we'll go through that. And in addition, whenever you talk about columns, you need to know what is effective length of a column. That is given in annexure E, effective length of columns. Okay, depending on the framing, please note that these columns are going to be connected at the top. A column may be connected to the top, at the top to another column, or several beams may be framing into the column at each of the, at either end of the column, depending on the stiffnesses of the columns and beams that are framing into. The column can have, or the behavior can be different under different kinds of these framing elements. Okay, depending on the stiffness of the framing elements, end conditions may differ, so effective length may be different. So figure 26 and 27, they are giving the effective lengths for two types of columns. A column which is in which sway is allowed, and when the sway is prevented. Okay, so effective length ratios for a column in a frame with no sway in the sense lateral, it moves in the lateral direction. There is a possibility. Okay, so when there is no sway, what is the effective length fact? This is the effective length ratio. This ratio you need to multiply with the length of the column, that gives you the effective length. You can make use of table, figure 26 and 27. This is for a column which is restrained against, or so without restraint. Sorry, this table 27 is a column without restraint against sway, and this is no sway. This is restrained against sway. Table figure 26 is giving you effective length ratios for column without sway, and 27 is giving you the effective length ratios for column with sway. And also this is depending on the framing system. But if you like, you know, these are the effective lengths for columns. These effective lengths you must have seen as a part of your mechanics of materials or structural analysis course. Depending on the end conditions of the column, effective lengths for different end conditions, they are given here. Theoretical value, as a part of your mechanics of materials or structural analysis, you must have studied, or you must have noted the theoretical value of effective length, this column. And for design purpose, what is the recommended value of effective length as per IS code? This is theoretical value, and it is this effective length is slightly increased. Please note that when effective length is slightly increased, this the capacity of the column is going to get reduced. So for design purpose, IS is recommending for some cases a slightly higher value of effective length. Okay, and these are the theoretical values. These values you can actually derive them from your simple concepts that you learn as a part of your structural analysis or mechanics of materials. So these are the things that we'll be using. Page 48, 49, 50, and page 70, 71, 72, and also this annexure E of IS 456 when we are looking at the design of these columns. Okay, so let's see some information related to columns. So structural concrete members in compression are generally referred to as columns and struts. Okay, structural concrete members in compression are generally referred to as columns and struts. The term column is associated with members transferring loads to the ground, and the term strut is applied to compression members in any direction, such as those in trusses. Okay, there is a typing mistake here. IS 456-2000 code defines column as compression member, as a compression member, the effective length of which exceeds 3 times the least lateral dimension. Let's go and see this class 25.1.1. Here, column or strut is a compression member, effective length of which exceeds 3 times the least lateral dimension. Okay. Again, short and slender column members. We will see all this in a while. Okay. The term pedestal is used to describe vertical compression member whose effective length is less than 3 times the lateral dimension, least lateral dimension. When the effective length exceeds 3 times least lateral dimension, that is referred to as column or strut, and if it is less than that, that is referred to as pedestal. Okay. Axially loaded columns may fail in any of the following modes. Okay. Pure compression failure, because as a part of design we need to take care or we need to make sure that the column is not going to fail in the possible different modes. That's why we are noting down in what type of modes or what kind of modes column may possibly fail. Axially loaded columns may fail in any of the following 3 modes: pure compression failure, combined compression and bending failure, failure by inelastic stability. Inelastic stability is nothing but by buckling. You must have learned as a part of your analysis, structural analysis or mechanics of materials, what is buckling. Okay, inelastic stability is nothing but buckling. But usually this failure by inelastic stability may not occur in reinforced concrete columns. Okay. Let's see this. The failure mode depends primarily on the slenderness ratio of the member, which in turn depends on cross-sectional dimensions, effective length, and support conditions of the member. Slenderness ratio, the failure mode. What type of failure mode? It's going to depend on the slenderness ratio. Slenderness ratio in turn depends on the cross-sectional dimensions, effective length, and the support conditions of the member. So let's see here, IS 456. Slender, short or slender compression members. Just now we noted this failure mode is going to depend on the slenderness ratio. Okay. What is that? What is that slenderness ratio? Let's make a note of it. A compression member may be considered as short when both the slenderness ratios. What is the slenderness ratio? It's nothing but L, effective length of column in the x direction, divided by the least lateral dimension, or D. D is nothing but, let's see what is D. D is the depth with respect to the major axis. Please make a note of it. D is the depth with respect to the major axis. B is the other dimension. B is the other dimension, width of the member. Okay. So, and what is X? X is major axis, Y is minor axis. Effective length with respect to the major axis divided by depth with respect to the major axis. Okay, here LEX, LE is to denote effective length, X is to just emphasize with respect to which major axis. Effective length with respect to the major axis, with respect to which axis? X is for major axis, Y is for minor axis. LEX is effective length with respect to major axis. LEY is effective length with respect to minor axis. Corresponding depth, okay? Depth with respect to the major axis. Width of the member is nothing but depth with respect to the minor axis. So you take the ratios. When both these ratios, which are referred to as slenderness ratios, are less than 12, then it can be classified as short compression members. And there is a reason why we are actually classifying them. Okay, it shall otherwise be considered as a slender compression member. Slender in the sense when this ratios exceeds 12, then they are slender members. When these ratios are less than 12, then they are short members. Okay, and there is a reason why we are classifying this, because if you go back or if you go to this limit state of collapse under compression, axially loaded columns loaded members in compression. Okay, and here actually the members subjected for short columns and long columns, we have separate kind of design. So for that we will be making that classification. Okay, anyway, we'll come back to this in a while. So depending on the failure modes, pure compression failure, combined compression bending failure, failure by inelastic stability, and then failure depends on the slenderness ratio of the member and also cross-sectional dimensions, effective length, okay, and support conditions of member. And depending on the reinforcement, I told you the transverse reinforcement can be in the form of tie, like this one, or you can have a spiral. You can see what is meant by a spiral here. Okay, it's starting here, and please note these ties are independent ones. Each of these ties are independent, whereas this spiral is continuous. So a column which has ties or a spiral as a lateral reinforcement, or this is also called helical reinforcement, or if the load that is coming on the column is becoming very large, and when you are designing, if your cross-sectional dimensions are becoming larger and larger, then when you have space constraint, then you can go for this kind of composite column. A composite column is a column in which a size of the column can be reduced by actually including a steel section like this, I section. Okay, you can see here I section is placed around which you have these ties and also longitudinal reinforcement and concrete. Rest of the portion is concrete. So you can have a composite column or any of these kind of things. Okay, so columns can be classified based on the type of reinforcements in this manner. Anyway, as a part of this course, maybe we will be studying this the first one and also second one. Okay, depending on the type of reinforcement, just now we noted in the figures, description is given here. Reinforced columns are classified into following three groups: tied columns, in which main longitudinal bars are confined within closely spaced lateral ties. Spiral columns having longitudinal reinforcement enclosed within closely spaced continuous wound spiral reinforcement. It's continuous spiral reinforcement, continuous helical reinforcement. Composite columns in which longitudinal reinforcement is in the form of structural steel section or pipes with or without longitudinal rebars. Whatever figure we have seen in that, longitudinal reinforcement are also shown for generality, and also you have the ties. In general, tied columns are the most commonly used, having different shapes. Whatever columns you see, mostly they are tied columns. You can have different shapes. Okay, from architectural considerations or from some other reason, okay, columns can be of square shape, rectangular, T, L, circular, etc. Spiral columns are adopted with circular cross sections and also for square and octagonal sections. And based on the type of loading, columns can be classified, or the loads that are coming on the columns can be classified in this manner. Axial loading alone, or load with respect to eccentric with respect to one of the axes. Okay, uniaxial eccentric loading. Load is eccentric with respect to only one axis, or load can be eccentric with respect to both axes, major axis and minor axis. Okay, type of depending on the type of loading. And here it's going to be subjected to pure compression. Here it's going to be subjected to compression as well as uniaxial bending along one of the direction, bending with respect to one of the axis. Here bending is going to happen with respect to both the axes. So axial compression along with bending along both directions. Depending on the type of loading, columns may be classified into following three types: axially loaded columns, supporting concrete loads. Axially loaded columns supporting concrete loads are relatively these axially loaded columns are really rare. Okay, interior columns of multi-storied buildings with symmetrical loads from floor slabs from all sides are common example of this type. Usually you will not have only pure axial compression. Okay, column with uniaxial eccentric load are generally encountered in case of columns rigidly connected to beams, or the outer columns. Okay, the columns which are on the periphery of a framing system, they are subjected, or they are going to be sometimes they are of uniaxial type. Okay, columns with uniaxial eccentric loadings are generally encountered in case of columns rigidly connected to beams from one side only, such as edge columns. Columns with biaxial eccentric loading is common in corner columns with beams rigidly connected at right angles to the top of the column. Or if the load or is not with respect to along one of the direction, if the eccentricity is with respect to two directions, why that is going to happen depending on the layout and other things. Okay, eccentrically loaded columns have to be designed for combined axial force and bending moments. So that is what in the code this section is giving here. Short axially loaded columns in compression. We know when the columns are short, when the columns are slender. So this particular section is giving you details about short axially loaded members in compression. And this particular section is giving for when you adopt lateral ties and when you adopt helical reinforcement or spiral reinforcement, compression members with helical reinforcement. This particular class is giving, this particular section is giving the details about that. And members subjected to combined axial and uniaxial bending, they are given under this. Okay, 39.6 and 39.7 is talking about slender compression members. We noted how to classify compression members as slender or short. As a because of lack of time and other things, maybe we'll focus as a part of this basic course, we'll be focusing only on the axially loaded members in compression with the ties as well as helical reinforcement. We may not be able to cover this one. combined axial and uniaxial bending or slender compression members. Okay. So we will be making use of these particular sections of the code. And now for completeness, once again, let's go through this. Columns can be classified based on slenderness ratio. Columns may be classified as short columns, slender or long columns. And the classification is based on the slenderness ratio. Just now we noted in the referring to IS 456 as well. The slenderness ratio in both directions should be less than 12 to be classified as short column. If any of the ratios, if any of these ratios, that is Lx divided by D, Lx, Ly, Lex divided by D, Ley divided by B, if any of these ratios is equal to or more than 12, then it is termed as slender or long column. This definition is not suitable for non-rectangular, non-circular columns where slenderness ratio is better defined in terms of radius of gyration rather than lateral dimensions. Okay, and as a part of steel design course, usually in steel design we will be making use of this radius of gyration. Okay, anyway, you just make a note of it. Maybe we may not have time to go in detail on this particular statement. Okay, so the slenderness ratio is not suitable for non-rectangular, non-circular sections. Or this definition with respect to Lex divided by D, Ley divided by B, this kind of classification may not be suitable for non-rectangular, non-circular cross sections. So now let's see what is the effective length of a column, how it is defined. Effective length of a column depends upon the unsupported length, distance between lateral connections, and the boundary conditions at the end of column due to the conditions of framing beams and other members. Please make a note of it. Okay, effective length of a column depends on unsupported length, distance between lateral connections, boundary condition at the end of column due to the conditions of framing beams and other members. Framing beams as well as the other members, in the sense the column on the top and other things. Okay, so if you make a note of this point, then we can go and see IS 456 annexure E. So here you can see here, let's read this as well. In the absence of more exact analysis, the effective length of columns in framed structures may be obtained from ratio of effective length to unsupported length. LEF, it is written as effective length to the unsupported length. Here, this is given. Unsupported length is nothing but the distance between the lateral connections. Distance between the lateral connections is the unsupported length, and this effective length ratio is defined as what is the effective length of column to the unsupported length. What is that value? That depends on certain parameters, beta 1, beta 2, depending on whether the column is a no sway column or sway column, a column which undergoes sway. Okay, so now let's see this one. In the absence of more exact analysis, effective length of column in frame structure may be obtained from ratio of effective length to unsupported length given in figure 26. This one. When relative displacements of ends of column is prevented. When relative displacements of ends of column is prevented. Two ends of the column, top and bottom end. When the relative displacement between the two ends is prevented, that is no sway. Okay, that is what is meaning of no sway. There is no relative lateral displacement between the two ends. Relative displacement of the ends of the columns are prevented. For that case, make use of figure 26. And there is a typing mistake in the code. This is figure 27. In figure 27, when the relative displacements of the ends is not prevented, when there is like possibility that there is going to be relative displacement between the two ends, then that type of column is classified as a sway column. For sway column, what is the effective length, ratio of effective length to the unsupported length? That is what is effective length ratio. Here also there is a typing mistake. It should be LEF, effective length. Here you can see effective length ratio. Okay. Anyway, beta 1, beta 2. We need to understand what is this beta 1, beta 2. Okay. And also, in the later case, it is recommended that the effective length ratio may not be taken to be less than 1 point. That is, the columns in which can be classified as no sway. Okay. Without any restraint against sway. Sway column. Sway column effective length shall not be less than 1 point. May not be taken less than 1 point. Effective length ratio. And how to read this figures 26 and 27? You can see here on the horizontal axis you have beta 2 and on the vertical axis you have beta 1. You need to know what is this beta 1, beta 2 to read this figure and get effective length ratio. What is this beta 1? What is this beta 2? Similarly for this figure 27, beta 1, beta 2. So this beta 1, beta 2 depends on whatever is mentioned here. In the slide it is mentioned the effective length of column depends upon the unsupported length and the boundary conditions at the end of the column, at the ends of the column. Two ends of the column, what are the boundary conditions? Due to why these boundary conditions are going to be different? Due to the conditions of framing beams and other members. What are the beams that are framing into that particular end of the column, and what are their stiffnesses? So beta 1, beta 2 are given by this. Sum of all columns, sum of all stiffnesses of columns. Kc is nothing but Kc is flexure or stiffness of the column, flexural stiffness of the column. The stiffness of the sum of all the stiffnesses of the columns that are framing at that particular end. Okay. Each end may be having different number of beams framing into it. Okay. So beta 1 is for the top. You can say it is a top, the top of the column, and beta 2 is bottom of the columns. And these two need not be same. You need to calculate beta 1, beta 2, you need to know stiffness of columns and stiffness of beams. And how to get this stiffness of columns, stiffness of beams? You need to go back to your structural analysis and then try to get what is this stiffness depending on the support conditions of beams and other things, and the support conditions of the columns. So this Kc, sigma Kc is nothing but this flexural stiffness of all the columns that are framing at that particular joint, top and bottom. Based on that, you calculate beta 1, beta 2, and then read from this figure what is the effective length ratio. Anyway, we may not be able to go through all those details, but for completeness, I'm showing you. Okay. And also, this is how you need to read this beta 1 using beta 1, beta 2 figure 26, 27. And also 26 is for no sway column and 27 is for sway column. How do we classify this? How do we say whether a column is sway column or a non-sway column? To determine whether a column is no sway or sway column, stability index is given by the code. Code is giving some stability index, and if the stability index is less than 0.04, column in the frame may be taken as no sway column, otherwise column will be considered as sway column. So you need to do, first you need to find the stability index. Given a framing system, you need to find the stability index. Once you get the stability index value, you can classify it as a sway or no sway, and correspondingly you can make use of either figure 26 or 27. Okay, so these are the details that go into the reading of the effective length ratio for a particular framing system. But we may not have time to go through all that in this course, basic course. We for completeness, I'm showing you. But as a part of this course, we'll be making use of this effective length of compression members. Okay, degree of end restraint of compression members. You can see here fixed, and fixed and hinged. Okay, hinged, and fixed and free. Okay, and here this is held in position. The top end is held in position, but relative movement is allowed, and the top end is not held in position. That is this case. Okay, and this is hinged, and the top end is held in position, and fixed and free. For various end conditions, what is the theoretical value of effective length? What is the recommended code IS 456 recommended value for the effective length? We will not be going in detail on this procedure for calculating effective length, and maybe we will stick to this one. Okay. So just for completeness, that one.
I would just add here. See, please note in the top three figures, the column is not swaying, and hence the effective lengths are limited to the effective length divided by the unsupported length ratio is limited to 1. Whereas the bottom four figures, these columns are considered to sway. That means the top is moving with respect to the bottom laterally. And you see that the values of this ratio of the effective length to the unsupported length is more than 1. That means this corresponds to the previous charts. Just for curiosity, you should see that essentially these values can be picked up from the previous charts also.
Yes.
Okay.
Anyway, the one point I showed you that for sway columns, here in the later case is nothing but corresponding to figure 27. There is a typing mistake. It is 27. 27 is for sway columns. It is recommended that effective length ratio may not be taken less than 1.2. This statement is what Professor Amlan is referring with respect to the values that are given here. Here, these three are non-sway and these are sway columns. In sway columns, even as per that statement, the effective length ratio shall not be less than, but it should not be taken less than 1.2. So he is pointing out to that. Here you can see here effective length ratio is more than. Actually, this is not effective length ratio, it is effective length. This is L is unsupported length. Here, unsupported length of compression member and multiplied by with some factor. That factor is not less than 1 point. Okay. And whatever just now we noted, anyway, that's all written here for completeness. Effective length. Effective length is some factor K multiplied by unsupported length. Effective length ratio or effective length of compression member depends on bracing upon bracing and end condition. Bracing in the sense whether there are external bracings or depending on the framing system whether the column undergoes sway or no sway. Okay. For braced columns, laterally restrained at ends, the effective length is less than the clear height between the restraints, whereas for unbraced or partially braced column, Effective length is greater than the clear height between the restraints. Please make a note of this point. Whatever table we have seen, table 28, you can apply to that and see. For braced columns are the columns when there is no sway. For no sway columns, effective length is less than the clear height between the restraints. Clear height between the restraints is nothing but unsupported length. So that coefficient K is going to be less than 1. For partially braced or for unbraced or partially braced column, the effective length is going to be greater than the clear distance between the restraints. So you can see here in this here, this coefficient is less than 1 or at most equal to 1 for no sway columns, and for sway columns this is more than 1. Okay, and few more points. Slenderness limits. Column dimension should be selected in such a way that it fails by material failure only, not by buckling. You can see here we have noted 3 types of failure modes: failure due to compression, failure due to compression bending, and inelastic stability. Inelastic stability is nothing but buckling. So the column dimension should be selected such a way that it fails by material failure only, not by buckling. To ensure this criteria, code recommends the clear distance between the restraints, unsupported length, should never exceed 60 times the least lateral dimension of the column. That is given in class 25.3.1. Let's see that. Unsupported length of the column. Okay, unsupported length of column. Let's see where it is. 25.3.1. Here, unsupported length of columns between the end restraint shall not exceed 60 times least lateral dimension. Because once you decide on the, please note that as a part of design, you may be recommending the section dimensions as well as the reinforcement details. So you need to make sure, or you need to do this check. Unsupported length between the end restraint shall not exceed 60 times least lateral dimension. If in any given plane each end of column is unrestrained, its unsupported length shall not exceed. These are the checks that you need to make before you release your design. Okay, slenderness limits on the columns. And B is the width of the cross section, D is the depth of cross section measured in the plane under consideration. And also column should be designed for minimum eccentricity. All columns shall be designed for minimum eccentricity equal to unsupported length of column divided by 500 plus lateral dimension divided by 30, subjected to a minimum of 20 mm. Even if the column is subjected to axial load, you need to design for minimum eccentricity. Where biaxial bending is considered, it is sufficient to ensure that the eccentricity exceeds the minimum about one axis at a time. Okay. Anyway, when we are designing, you will understand better. So whatever I just showed you, the points that are given under this 25.3.1, they are written here, and also minimum eccentricity, whatever I showed you in the code, that can be written in the form of an equation. You please make a note of this one. Unsupported length divided by 500 plus least lateral dimension in the plane of bending divided by 30. That is the minimum eccentricity to which we need to design, but not less than 20 mm. Please make a note of this. And this is for rectangular columns. For non-rectangular, non-circular cross sections, SP24 recommends the minimum eccentricity as L effective length divided by 300 or 20 mm, whichever is greater. Please make a note of this. Okay. So in broad sense, we already noted all the points that are required for designing at least a short column. Okay. Anyway, we already noted this one. And I mentioned to you as a part of this course, we may not be, because of lack of time, we may not be able to go in detail about all these stability index and other things. So we'll skip this one and directly note down the procedure for short columns. And I will just outline you the procedure for short columns, and then we'll stop there and continue in next class. So let's see the procedure for short columns. Limit state of collapse under compression. First, we need to make a note of the assumptions, okay? And please note that these compression members or columns can be subjected to pure axial load or axial load plus uniaxial bending or biaxial bending, okay? So the assumptions for the design of columns, it includes the assumptions given in 38.1 A to 38.1 E for flexure. It includes whatever assumptions we noted for limit state of collapse under flexure. In addition, okay, the following are also assumed. In addition to the assumptions given in 38.1 A to 38.1 E for flexure, the following shall be assumed. And let's go and see the assumptions for made under flexure. Plane sections normal to the axis remain plane after bending. That is one of the major assumptions for a member which is undergoing flexure. Maximum strain in concrete at outermost compression fiber is taken as 0.2035 in bending. Okay, and based on that, we have noted stress block and other things. Those details are given here. And also based on the stress strain relations, we noted these relations. Okay, and also we noted tensile strength of concrete is ignored. Okay, so in addition to these assumptions, let's see what are the assumptions that are made here under limit state of collapse in compression. Maximum compression strain in axial compression is taken as 0.202. You need to make a note of it. Maximum compressive strain in concrete in axial compression is limited to 0.202. Whereas here, maximum strain in concrete is taken as 0.2035 in bending. Okay, that is one assumption. And the other assumption, maximum compressive strain at highly compressed extreme fiber in concrete subjected to axial compression and bending. And when there is no tension in the section, shall be 0.2035. Please note that when the section is subjected to axial load plus bending, as a part of your mechanics of material, you must have studied that a part of section can be in tension, a part of section can be in compression. Okay, so this assumption is referring to that. The maximum compressive strain in highly compressed extreme fiber in concrete subjected to axial compression and bending, and when there is no tension on the section. So the entire section is in compression or zero value of compression. Okay, shall be when there is no tension on the section shall be 0.2035. Please note it as an equation. Okay, 0.2035 minus 0.75 times strain at the least compressed extreme fiber. Okay, so the maximum compressive strain is you need to make sure is limited to this one. So what is the explanation for this? You can refer to SP16. SP16 is nicely elaborating on that. let me show you that. Here, this is highly compressed edge. This is highly compressed edge, and this is what it is referring to. And the details of it, what is the elaboration on that is given here. If somebody is interested, they can go through this. Or let me quickly point out to this. For purely axial compression, strain is assumed to be uniformly equal to 0.202 across the cross section. Okay, and when there is this, when there is a bending as well as compression, then the strain in the highly compressed edge is 0.2035 minus 0.75 times the strain at the least compressed edge. So this is all coming from this strain diagram, strain distribution diagram. Okay, and also based on this identification of fulcrum and other things, where where it is changing, where this is pure compression. Anyway, the details we may not be able to go through the details, but just to make a note of that assumption. Okay, because of lack of time. And the minimum eccentricity, we already noted minimum eccentricity that we need to use for columns. And just let's go through this and then we'll stop there. Short axially loaded columns in compression. Okay, members shall be designed by considering assumptions, whatever we have noted, 38 under 38 section as well as 39. And also we need to design for minimum eccentricity. When minimum eccentricity does not exceed 0.5 times the lateral dimension. When minimum eccentricity is not exceeding 0.5 times the lateral dimension, the members may be designed by the following equation. So, as a part of this basic course, we'll be making use of this equation. And please note that whatever you are learning as part of this basic course, that is valid only when the eccentricity, minimum eccentricity is not exceeding 0.05 times the lateral dimension. And this PU is nothing but axial load on the column. Or if the reinforcement and the section details are given to you, if reinforcement, section details, grade of concrete, grade of steel are given to you, you can estimate the capacity of this section. Or if the axial load is given, you can make use of this equation and try to find what should be the area of concrete and what should be the area of compression reinforcement. And how this equation is obtained? This equation is obtained based on these assumptions. Okay, so we'll go through this and the details. PU is axial load on the member, FC is grade of concrete, FY is grade of yield strength, characteristic strength of compression reinforcement. ASC is the area of steel in compression. AC is the area of concrete. Okay, and this is the capacity of a column when you have lateral ties. The strength of the compression member with helical reinforcement. If instead of lateral ties you provide helical reinforcement, then you can enhance this capacity. PU you can enhance it by 5%. The strength of compression member with helical reinforcement shall be taken as 1.05 times the strength of similar members with lateral ties. Okay, and how to provide this helical reinforcement? Some clause is there. We'll go through it in the next class. So we'll limit our study to this portion: axially loaded, short axially loaded members in compression. Okay. I'll stop here. Professor Amlan, you want to add something?
Yeah, I should just mention that, see, whatever loading we are considering, that is under gravity loads. It means a column under axial load may be subjected to bending under lateral loads. That's why, in general, we typically always consider some bending also. Okay.
Okay, thank you. Any questions? Okay, thank you. We'll meet on Tuesday for the last class.